Hello everyone, welcome to the 28th lecture in the series. In this lecture, we are going to learn about some of the traversals associated with this graph data structure. When we learnt about the tree data structure, we learned some of the traversals associated with trees, namely in-order traversal, pre-order traversal and post-order traversal. And we learnt that the purpose of those traversals are to impose some ordering of nodes or vertices in that tree. So, similarly, we have two traversals here, one is breadth first search and other one is a depth first search, and those two traversals we will be learning in detail with examples, and after that we will be going on to learn one of the sorting associated with graph, namely topological sorting. So, next let us see each one of them in detail with the further slides. So, first is the graph traversal algorithm. So, for traversing tree, as I said, we use all of these three traversals, and for graphs also we have certain traversals, and the objective of the traversal is to start from one start vertex or node in a graph and possibly trying to reach all other vertices in that graph. And if suppose your graph is disconnected, a graph traversal can begin at any one node and will try to visit all the other nodes that are part of the same connected component. And in order to reach the other parts of the same graph, we may again have to fix up some other vertex as start vertex in that connected component and try proceeding to reach the other vertices in that graph. So, these are the two basic traversal algorithms that we can use for graphs. One is a depth first search, which we will call it as DFS hereafter, and the other one is a breadth first search, which we will be calling as BFS hereafter. So, in a depth first search, what we do is that we will fix up a start vertex and then we will proceed to go deep into the graph in search of vertices that are not yet visited. Once we have gone to that depth in such a way that we do not have any edges to proceed further, at the time we stop there, backtrack and try to find whether there are still any vertices left in that graph that are yet to be visited. If you proceed in that fashion, then that search is called as a depth first search. In case of a breadth first search, what we do is that we will fix up a start vertex, then we try to reach to other vertices that are all adjacent to it. So, that are all adjacent to it in that sense, those vertices that have an edge from the start vertex to themselves can also be treated as adjacent vertices. So, we will mark them visited, and once those adjacent vertices are visited, then we will try to fix any of those vertices as the next point to start, and from there we proceed with looking at vertices that are adjacent to the set vertex. Likewise, we continue to do this till we reach every other vertex in that graph. So, this way of visiting every node or vertex in a graph, we call it as a breadth first search. So, this is how your breadth first search strategy works. So, we say that the breadth first search works in level order. So, already we have learned this with respect to trees. You could visualize by this time the way we represented trees, and we called every level in a tree, and we hope you remember by this time we used to call the root node in a tree is present at level 0, and we continue to label other levels in the trees from 1, right. So, here what we say is that in a breadth first search we always look at the level order and we visit the nodes in the graph level by level. Say for instance, from node level 0 we will try to visit all the nodes that are all at level 1, which means those vertices are reachable from the start vertex exactly by one hop, and we continue to do the same for every levels in your graph. Say for instance, if V is our start vertex, we visit all of V's neighbors and then we visit all V's neighbors. Likewise, we continue to do depending upon the number of levels we have in that graph. And in order to make this possible, we normally use a queue and once we start from the start vertex V, we take up all its neighbors and put up in a queue, and then we remove one of the vertices from a graph and mark it visited. Likewise, we continue to do for all other neighbors. After visiting all the, while we mark one of those neighbors as visited, then we try to look at its neighbors and try to add those neighbors to the end of the queue. So, we will continue to do this till every vertex in that graph is said to be marked. So, the breadth first search can be implemented following this algorithm. So, first is that we create a queue and then we add the start vertex, and then we mark the start vertex as visited, and then we check whether the queue is not empty, and if not empty, we will dequeue one entry from the queue, and then we check the nodes, let us assume that the dequeued element is W, then we check what are all the vertices that are all reachable from W or that are all adjacent to W. So, each of those unvisited nodes alone are then added up in the queue, and then we will mark one of its neighbors, that is U, as visited, and likewise we will proceed to do this till we mark all the nodes in that graph as visited. So, this is a very simple example that we have for a breadth first search. Consider a graph. This is an undirected graph with 5 vertices. So, as you know, we have we are going to process this graph level by level. So, here our start vertex is assumed to be 5. So, from this graph you could see that from 5 we have vertices V3 and V4 as reachable. So, those two are the nodes that have to be visited next to the start vertex. So, while I say for instance I have the possibility to consider either V3 or V4 now. Imagine that I have considered V3. So, from V3 I could reach either V2 or V4. So, again as V4 is not visited by this time, then I can then try reaching out V4, and when V4 is considered, then V3 and V2 and V5 are all reachable from it, but of course by this time V3 and V5 are already visited. So, my next choice would be to go to V2, and from V2 there is only V4 and V1 reachable, but V4 is already visited, and so finally as a last step we reach out to V1. So, by this time there are no more vertices yet to be visited, and so we can stop this breadth first search, and so we call this kind of traversal, that is we have visited all the 5 nodes in the graph, and so we can call this as a kind of traversal. So, for doing this we have made use of queue, and initially we have the start vertex as V5, and only the start vertex is added up in the queue. Then we dequeue. So, when we remove V5 from the queue, then we are supposed to add its neighbors or adjacent vertices. So, likewise we have added V3 now. When we mark V3 as visited, then we bring in V4, right. So, by the time when we add V4, V3 and V4 are its neighbors, and so it is part of, it's in the queue, right. So, we keep on doing this by adding its neighbors every time. Whenever a vertex is marked visited, its neighbors are all added up to the queue, provided they are not visited yet. So, we will continue to do this till we reach the last vertex, which is V1. So, here this is again an explanation for breadth first search. Given a source vertex, we try to explore the graph G and try to discover every vertex that is reachable from the start vertex. So, we compute the distance from S to the reachable vertex, and the result of doing a breadth first search would be a breadth first tree with root as the start vertex, and it will contain all other vertices that are reachable from it. And there is a possibility that we can compute the shortest path from S to every other reachable vertex. So, the result of breadth first search would be a tree, and we call that tree as a breadth first tree. So, your breadth first search would help you to discover all vertices which are actually at a distance k from S, and after, just because it works in a level order fashion. So, we first consider vertices that are all at a distance k, and as a next step we would consider vertices that are at a distance of k plus 1. So, we proceed to continue this way. Next would be k plus 2 and so on. So, here this is the how your breadth first tree would look like for a vertex like this. So, here in this breadth first tree BFS tree, you could see that 0 being the start vertex. So, we can assume that from 0 our next consideration would be vertices at a distance of k. In our case, let k be 1. So, here vertex 2 is at a distance of 1, vertex 4 is at a distance of 1 and vertex 1 is also at a distance of 1, and those 3 vertices will be visited next, and at last its neighbors have to be visited. So, 1's neighbors are 4 and 0, but 0 is already visited. So, we ignore, and 4 is also already visited. So, this has to be ignored. When you consider 2's neighbors, it is going to be 9, 10 and 4. Of course, 4 is already visited. So, we ignore. So, next step we will consider 9 and 10. Likewise, for 4, so there is one more vertex here which is 5. So, 5 is also neighbor of 2. So, all those 3 vertices have to be considered as the next step. So, when you look at it from the start vertex, 1 to 4 are at a distance of k and 5, 9, 10 are all at a distance of k plus 1, and likewise it continues, right. So, the resultant tree we call it as a BFS tree. So, this is the traversal, I mean the routine in order to perform a breadth first search. So, here we have this is what we do for every vertex we. So, initially this is kind of initialization, we initially mark all the vertices as not visited, which means visited of v is set to false. Then for every vertex we try to if it is not visited yet, then we make an call to the procedure BFS of v. Within BFS of v, what we do is that first we mark that vertex as visited, we enqueue all of its neighbors, then while not empty of queue, we will dequeue one of its entries, mark it visited, and then we will add all other adjacent vertices into the queue provided they have not yet been visited. So, we will continue to do this till all the vertices are marked as visited. So, when you look at the complexity of this particular breadth first search algorithm, it is going to be of the order of n plus e, where n corresponds to number of vertices that you have in that graph, and because for every vertex, for every edge that is associated with the vertex, we will be computing whether it is visited or not, and so its complexity is order of n plus e. The next kind of traversal that we can do is that it is a depth first search. The name itself says we are going to search deeper and deeper into the graph if possible. So, here we will have a start vertex and we will try to explore edges deeper and deeper. So, while doing so, we will check whether the vertex has been marked visited or not. If not, we will try to go even more deeper. When all the edges in the graph have been marked as visited, we can finish, and if in case there are still some vertex that are to be marked visited, then we may have to backtrack if there is no way of going forward deep down into the graph. So, we will be continuing this process until all the vertices are marked visited. If suppose even after doing this there are some vertices which remain undiscovered, then there could be because of the reason for there are connected components in that graph. So, if there are connected components, which means there is some sort of disconnectivity in a graph and the graph as such appears in pieces. So, in that case you may have to fix up a new start vertex and then proceed this visiting these vertices in a depth first version for that connected component. So, as such, if suppose your graph is not connected, or if it appears as a set of connected components, your DFS will create a forest of DFS trees. So, as such, like we had a BFS tree as an output for BFS search. So, here in case of DFS also the resultant would be a DFS tree. If there is only one connected component in your graph, then there will be one DFS tree. If your graph contains multiple connected components, then the resultant will be a forest, which means a collection of DFS trees. So this is how the routine for DFS would look like. We will initially mark select an unvisited node, then mark it as visited and treat it that as a current node, and you then look at any of its neighbors. If it is unvisited, you just go and mark it visited, make it the current node and mark it visited. Likewise, we will proceed going down and down or deeper and deeper into the graph. At one point of time, you will end up in a situation where you don't have any other vertex to locate that is not visited, and so you may have to backtrack and find some other alternate path through which you may be able to visit a vertex that is not yet visited. So, we will be repeating steps 3 and 4 until more of nodes are marked visited, and if suppose there are still unvisited nodes, we may have to repeat from step 1 provided from a different connected component. So, this is your illustration for or example for a depth first search. So, here too in the resultant of a depth first search would be a DFS tree. Here you could see that the start vertex is 0 here. So, which means I had started, I had attempted to do a DFS starting from this vertex 0. From 0 I took turn to visit node 1, from 1 to 4, 4 to 2, 2 to 9 in our case, 9 to 11, 11 to 10. After that I end up reaching 2 only. So, but I cannot consider because it is a tree, should not have any cycles, so I cannot have 2 here, but there is no way to reach out to other vertices from 10. So, in that case I should come back to 11 and check whether there is any other way of reaching out to other vertices. There is no possibility, so we backtrack to 9, no way of going anywhere, backtrack to 2. After reaching 2, there is a way from 2 to 5. We do not take this path because 4 is already visited. So, from 5 I can reach up to 7, 7 to 8, and then after that there is no other path. So, there is a cycle here, so I cannot take it, and so from 8 I backtrack to 7, there is no other way of reaching out to any other vertex. From 7 I backtrack to 5, there is no other way, but from 5 I can go up to 6. So, with that all other vertices in the graph are all marked visited, and so we put an end here. So, this is the resultant DFS tree. So, here we have one more example, which is a very simple one. We have a undirected graph. So, for here we had chosen V3 as the start vertex. So, from V3 we have gone to V2, from V2 we have gone to V1. From V1 there is no other way of going, backtrack, come to V4, from V4 we can reach up to V5. So, this is where it stops because we have marked all the 5 vertices as visited. So, here we are first looking at non-recursive version of DFS. So, when it comes to implementation of DFS, we usually use stacks, because you know that whenever there is backtracking, we are supposed to use a stack, only then we can move to the previous state. So, here initially we create a stack and then put the start vertex in, which is the V, and then we mark V as visited. Then when the stack is not empty, we will let X be the node on the top of stack. If no unvisited nodes are adjacent to X, then you make backtrack. For backtracking sake, you are supposed to pop out the vertex that was put up in the stack. If there is a way to go forward, then you move to the else part, where you select an unvisited node which is adjacent to X and then push that vertex onto stack. The reason for doing this push is that so we are actually marking the node as visited and then pushing it. The reason is that if suppose I cannot go anywhere forward from that particular vertex, I may have to come back from here and try to go in some alternate directions. That is why we keep on doing this. So, this is a non-recursive version of working on DFS. So, here this is how your non-recursive version works. So, initially V3 was our start vertex, we pushed on to stack, then we made an attempt to visit V2, and then we also added V2 to stack, then we visited V1 and added V1 to stack, and from V1 there is no way of going in forward direction, and so we backtrack to V2. So, for that backtracking sake we have popped out V2. So from V2 I had an option to go in forward direction to V4. So we mark V4 as visited, and V4 is also added to stack. Then we visited V5, so V5 is also added to stack. Now we backtrack, so we pop out and look at from V4 whether there is any other node to be visited. No way. So we again backtrack to V3. We check whether there are any other vertices that are yet to be visited. No. Then we backtrack to V2. Likewise, we backtrack till we reach the starting position and make a check whether all the vertices in the graph marked as visited. If so, we can stop this process, and the resultant would be a DFS tree. So, having learnt the various traversals that you could perform on a graph, now we move on to one kind of sorting that is permissible on a graph. So, for this sorting to work, the first condition is that your graph should be a directed and acyclic graph. So, we have learned the terminologies already. So, by this time you know what directed and acyclic graph mean. So, it is a directed graph means it is a graph containing edges with directions, and the graph is not supposed to contain any cycles. So, in a DAG we have linear ordering of all the vertices, and such that if it contains an edge u comma v, then u appears before v in the ordering, which means it is a directed graph. So, the graph edge starts from u and ends in v. That is what we mean as the ordering. So, we can do topological sorting, as I said, only if it is a DAG, and topological sorting is a way to order your vertices along a horizontal line, so that all the directed edges grow from left to right. So, that is the objective of doing a topological sorting. You know, any sorting puts your elements in order, right. So, in a graph we do this kind of sorting to put all your vertices in some order in such a way that just because it is a directed graph, we want all the edges to flow from left to right, and this ordering is made possible with the help of this topological sorting. Not only that, this directed acyclic graph in specific finds applications in many areas. Say for instance, whenever you want to indicate some precedence when you present some events, then in that case you can go for a directed acyclic graph. Say for instance, imagine that you are representing the courses that a student takes up in his career. So, here say for instance, course A has to be taken before course B, then there should be flow of, there should be an edge from A to B, right. So, that can be implicitly enforced with the help of a directed acyclic graph. So, here we have a directed acyclic graph. So, our topological sorting would actually put your graph in some ordering in such a way that if there is an edge from Vi to Vj, then normally Vi will appear before Vj in the ordering. And the complexity for doing this sorting is order of number of vertices plus number of edges. So, for doing this topological sorting, for implementing this topological sorting, we usually go for a queue. So, initially we pick up a vertex whose in degree is 0. In degree is 0 in that sense that vertex does not have any edges flowing into it. So, if so, the vertex in degree will be 0. We are supposed to pick up one such vertex whose in degree is 0 and then add it up to the queue. And after that we have to check, we have to do this till the queue is not empty, and what we do is we dequeue that particular entry, print it as visited, and we will look up what are all the vertices that are adjacent to it, and in every vertex that are adjacent to this vertex V, we will be reducing its in degree by 1. The reason is that we have removed one vertex from that graph. So, whatever edges that started from it will no more be part of that graph, and so we reduce the in degree of all other vertices that are connected to this particular vertex V, and after that we will be enqueuing those vertices into the queue. During the next iteration, what we would do is we would pick up another vertex whose in degree is 0. So, we will continue to do this till all vertex appear in our ordering. So, here as I said, whenever there is need to represent precedence, then we can go for topological ordering. So, here we have set of courses being represented in the form of a DAG, and here an arrow from A to B and A to E indicates that if B and E are treated as two courses, and for those two courses course A is a prerequisite. So for this reasons we normally go for a directed acyclic graph. So here as you know, for topological sorting we can also go this way of doing, like we can go for the concept of successor. So successor in that sense, if there is an edge from x to y, then x is called as predecessor and y is called as a successor. So we are supposed to pick up a node that has no successor. So this is one yet another way of implementing this topological ordering, and if you are able to find one such node, you are supposed to add it to the list, and we will be deleting all the edges that end up in that successor node, and we will continue to do this till all the vertices are marked or put into the ordering. So this is also yet another way of going for finding the topological ordering of vertices in a graph. So here the second way of looking at performing topological sorting is explained here. So with the concept of successor. So here the successor is that there should not be any vertex originating from a vertex, right. So here E is the, you could see here that in this case from D there is no outgoing edge from it, right. So here D has, we say that D has no successor, and so we are picking it up first, and then we remove edges that are getting into D, right. So we will be left with this only this portion of graph. Then we have to choose any other node for which there is no successor. We have two possibilities, B and E. For simplicity's sake, I am taken E as the next successor, E as the vertex with no successor, and then we will be removing the edges that are entering into E. So as such, this would be the resultant graph. Now you could see that the graph looks disconnected. So I choose C, and none of the edges have to be removed, just because C is already a connected component. And so next I move on to removing B, and finally I have to remove or choose A. So the topological ordering would be in reverse, that is A, B, C, E and D, right. So it just goes in the reverse version, and that is what we say as results. Alternatively, if I have to do it by the other approach which I mentioned before, you are supposed to choose the vertex whose in degree is 0. So in that case, for every vertex, say for instance C does not have an in degree, no other vertex entering it, right. Likewise for A also we do not have any edge entering into it, and but for B there is an edge entering into it. So B cannot be a choice, D also cannot be a choice, similarly E also cannot be a choice. So we have two possibilities, either to take A or C. Let us imagine that I have taken A. So after taking A, I have to remove edges emanating from it, so that we will have now two choices to choose, either B or C. So let me assume that I have taken B. I will be removing this edge. After that we will have only possibility as C. So I will be fetching C, because he will be the one with in degree 0. So while removing B, what you have to do is, till then D's in degree is 3. After removing B, we will be removing this edge also, and so D's in degree should be reduced by 1. So we will be continuing to explore this in the same fashion, and that will give you the same result, that is A, B, C, E and D would be the way this, that is the ordering of vertices in this particular directed acyclic graph. So you are free to use any of these two approaches for finding the topological ordering of vertices in your graph. So to summarize what we have seen so far, we learnt two traversals. One is a breadth first search and other one is a depth first search. In case of breadth first search, we try to explore vertices in a graph level by level, and for implementing this BFS, we go for a queue, and the resultant of a BFS would be a BFS tree. And the main aim of using BFS in a graph is to find the shortest path in case of an undirected or unweighted graph. And in case of the second kind of traversal, namely the depth first search, our aim would be to mark every vertex in that graph visited by diving deep into the graph. So, we will try to fetch one vertex and try to reach all other vertices that are that can be explored from it deeper and deeper. And this depth first search will also yield us a depth first search tree, and it is mainly used for detecting cycles in your graph and to put up ordering of vertices using a topological sorting algorithm, and for finding the connected component analysis. And for implementing this DFS, we normally go for a stack just because it involves backtracking. Both BFS and DFS traversals, they require a time complexity of order of V plus E, and in order to put the vertices in a graph in some ordering, we go for topological sorting. But to perform topological sorting on a graph, the graph should be, first of all, it should be a directed acyclic graph. And topological sorting can be done via two approaches. One is the DFS approach and another one is the in degree based approach, which I explained you with the previous slides and examples. And DFS is based on post order, and the in degree based approach is also called as it is based on Korn's algorithm. And the most important usage of topological sorting is that it is trying to help us to put the vertices in some ordering, mainly for ascertaining the precedence or prerequisite. The sorting helps a lot. And topological sorting will usually fail if your graph contains cycle. So, we mentioned that there is a prerequisite that your graph should be a directed acyclic graph. So, now having learnt the concept of traversals and sorting on a graph, let us have some questions to test our understanding of the concepts. One is, what is topological sorting and in what kind of graph is it applicable? So, topological sorting is basically to put vertices in a graph in some order. Possibly it puts the vertices in the order in such a way that the directed edges in such a graph would normally flow from left to right, and as such this kind of sorting can be performed only on a directed acyclic graph. How do you define a graph traversal as complete? When my DFS failed to visit all of the nodes. If suppose you have started from a start vertex on a graph and performed a depth first search, and if you are able to visit all the vertices in that graph by backtracking, then we can say that the graph traversal is complete and we have obtained a DFS tree. If suppose your graph has connected components, which means there are some vertices in your graph that are all left disconnected because of the absence of edges between certain vertices, and in that case your DFS will not complete because we have visited only a few of the vertices. In such scenarios, we may have to fix up another start vertex which is part of another connected component and proceed doing the steps once again. The third question is, can a disconnected graph have a spanning tree? Why or why not? So, if a graph is disconnected, then we will have more than one spanning tree, because for every connected component there could be one spanning tree. So, your resultant would be not a single spanning tree, but a it would be a forest or a collection of trees. Hope you are now thorough with the concepts that we have learnt as a part of traversals and sorting in a graph, and